Welcome to class today. We're going to talk about ionization energy and electron affinity, two important trends in the periodic table that tell us about the reactivity of elements. Starting with first ionization energy, we are going to see that it's going to help us to understand trends in the reactivity of especially metals, because metals are elements that lose electrons. And we're going to find first ionization energy as the energy needed to remove the highest energy electron from the atom in the gas phase. So we're going to take the atom X, add some energy. This is always going to be an endothermic process because we're removing an electron, and we're going to get the X plus ion and the electron. And we're going to use isolated gas phase atoms for this process because we want to eliminate the influences of any neighboring atoms. The first ionization energy trend is opposite to that of the atomic radius trend, but we're going to find out it's for the same reason that we have the atomic radius trend. As we move left to right across the period, it gets harder to remove the electron as the effective nuclear force, effective nuclear charge increases. And that's going to be because we have a smaller radius in the atom, and that smaller radius means the electron is closer to the nucleus. We have a stronger Coulombic attraction to the nucleus, and so the electron gets held more tightly, and we have a higher ionization energy. As we move up a column, the ionization energy also increases, and increasing as the radius decreases. So again, that outer electron, that very first electron that's easy to remove, is going to become going to become harder to remove as the electron gets closer to the nucleus in lower energy outer orbitals. Again, a stronger Coulombic attraction as we move up the column. There are some exceptions to the first ionization energy trend. As you can see in this graph, as we look at increases in the first ionization energy across periods, we see that along the bottom, all the alkali metals are the lowest ionization energy, have the lowest ionization energy in each of their respective periods, and the noble gases have the highest ionization energy in each of their periods. And you can see, for example, in the second period, going from lithium to neon, there's a general increasing trend as we saw in the previous slide. However, notice that as you come across, there are some places where there's a decrease in the ionization energy as we go from one element to another. The first time we see this is as we move from beryllium to boron, or magnesium to aluminum, zinc to gallium. And what's happening here is that when we populate an electron into the NP1, the first p orbital, that p orbital is more shielded by either the s electrons immediately preceding it, as in beryllium or as in boron and aluminum, or the d electrons, as in zinc or cadmium, immediately preceding it. So even though there's a slight increase in the nuclear charge as we move from one element to the next, that shielding decreases the Coulombic attraction of the last electron, and that makes that electron easier to remove. Likewise, we can see the decrease in the ionization energy as we go from nitrogen to oxygen, from phosphorus to sulfur, and a modest slight increase as we go from arsenic to selenium. And the reason for this is as we populate that fourth electron into the p orbitals, so oxygen, sulfur, arsenic are all selenium are all p4 electrons, the paired electron experiences electron-to-electron repulsion, and with just a slight increase in the effective nuclear charge, the paired repulsion acts as a decrease in the amount of Coulombic attraction to the nucleus, and so the electron in these atoms is also easier to remove. Now, there are subsequent ionization energies as well. Second ionization energy removes a second electron to make the X2+. Third ionization energy removes a third electron to make the X3+, and so forth. And you can see we can go up to even the 8th ionization energy, as you see for neon and sodium and magnesium here. If you take a look across each row, that you see that the ionization energy does increase moderately due to increased repulsion among the remaining valence electrons. I'm sorry, did I say increase? Decreased repulsion among remaining valence electrons. So that decrease in repulsion means that the nuclear charge is going to attract the electrons slightly more strongly, as you'd expect as you're trying to remove an electron from an increasingly positive environment. However, there are some places where we see large increases in the subsequent ionization energies. And that's going to be where we encounter core electrons. So for lithium, taking out the first electron is extremely easy, relatively easy. And then taking out the second electron becomes extremely difficult because we are reaching into the core electrons. The second electron from lithium is the helium 2s electron configuration, and so it's that electron that's in the 1s orbital. I said helium 2s, helium 1s2, and so that first electron that you're taking out of the 1s orbital is more strongly held than the first electron in lithium, the 2s1 electron. So that becomes harder. Likewise, with beryllium, we see that the first two electrons, which are the valence electrons, are easy to remove, and then a large increase in the third electron. Boron, first three electrons, those three valence electrons are easy to remove, and then the fourth electron becomes difficult. So as you come down the chart, you can see that every time we move from taking out a valence electron to taking out that first core electron, we get a large increase in the ionization energy, in that subsequent ionization energy. So this actually becomes a way for us to tell what column a particular element is in without knowing what the identity of the element is. So for instance, if I told you you had an element that had a large increase in ionization energy from, say, the fifth electron to the sixth electron, you'd know that that fifth electron was its valence electron, and the sixth electron was the first core. So you'd know 5 valence electrons, and then you'd know that it was an element in the nitrogen family. Without knowing more information, you can't know which row it's in, but you can tell which column it's in. And again, decreased shielding of the inner electrons leads to that large increase. And every time we go to a new inner core, we're going to see a large increase. But in general, we don't see anything beyond, we can't see ionization energies beyond these electrons, because it starts to become so difficult that the amount of energy you have to put in becomes essentially undoable in experiment. The opposite trend to ionization energy is electron affinity. Now, electron affinity isn't officially covered as a topic in the AP curriculum, but it does show up unnamed, and it also has some important effects on some of the other properties we're going to see. So we're going to talk about electron affinity so you understand a little bit more about it. The electron affinity is going to tell us about reactivity in nonmetals that gain electrons, because this is all about the energy change when an electron is gained by a gaseous atom. Again, the gas phase is necessary to isolate the atom from neighboring effects. The electron affinity is defined as the negative of the delta H, that enthalpy change. Wanting to keep the electron affinity positive when we have a positive, when we have a favorable electron affinity. Now, some books don't do it that way, but our book does. Our book will look at electron affinity as a positive when it's a very exothermic reaction. And thinking about exothermic again, we're going to remember that an exothermic reaction, an exothermic process, makes a more stable product, and it's more stable because the electron that's going in has a stronger Coulombic attraction to the nucleus than something that is less exothermic. The trend in electron affinity is generally the same as in the ionization energy, that the electron affinity starts off very low in the lower left-hand corner, as the electron that would go into the nucleus or into the atom is very, very far from the nucleus, and it increases as you move up. As that electron that you put in gets closer and closer to the nucleus, it becomes more stable, it becomes a more attractive environment for that electron. As you move to the right, the same thing is going to happen. We're going to see an increase in the effective nuclear charge. That increase in the effective nuclear charge is going to attract the electron more strongly. And also, because we're getting smaller, and remember the trend is that the radius gets smaller as you move to the right, because we're getting smaller, the electron is also getting closer to the nucleus, not just in a lower energy level. And so getting closer to the nucleus with a higher effective nuclear charge is going to increase the stability of that electron going into the atom. However, there are some exceptions to the trend, and this table shows you for the first 5 rows of the periodic table, excluding the noble gas, excluding the transition metals, what the actual electron affinities are, and these are listed in kilojoules per mole. And as you look across, you can see that there's some places where some columns in which the electron affinity becomes 0 or even negative. Now remember, negative means that the enthalpy change is positive, which means it's not favorable to put that electron into the nucleus, or into the atom. So where is that electron affinity, negative or 0? There's 2 places that are of interest to us. The first places are when you are going from the 2A to the 3A. So when you're taking a 2A electron, a 2A element, and you're putting an electron into that atom. So putting an electron into beryllium or into magnesium. Beryllium and magnesium are S2 electrons, S2 elements. And so that next electron is going into a p orbital. That p orbital is higher energy and is better shielded by the s electrons of the element. And so there's no real advantage, there's no real stability in putting an electron into that higher energy orbital. And indeed, it often does take some energy to put that electron in. Likewise, in 8A, in the noble gases, the electron is going to enter the next energy level. So neon is at 2p6. So the electron that goes into that is going to have to go into the 3s orbital. That 3s orbital is much higher in energy, and so there's no advantage, there's no stability in putting that electron into the 3s orbital. There's lower Coulombic attraction, and there's no and the electron affinity then is 0 or even negative for all of the noble gases. In column 5A, we have a similar thing, but we're not putting the next electron into a higher energy orbital. In nitrogen and phosphorus and arsenic, those are all P3 elements, and putting that next electron in is going to require pairing up that next electron. When we pair up that next electron, we get increased electron-electron repulsion because it has to go into an already half-filled orbital. So that electron-electron repulsion is going to decrease the attraction of that electron to the nucleus and is going to make it less favorable to put that electron into the atom. And there's one set of exceptions that occurs in the rows of the periodic table. You would think, based on what we know about reactivity, that fluorine, being in the second row and all the way to the right, except for the noble gases, would have the highest electron affinity. But it turns out chlorine is the one that has the highest electron affinity. And you can see this trend across the entire second to third energy level, where the third energy level has higher electron affinity than the second energy level, despite the electron getting closer to the nucleus in the second energy level. The reason for this is because the second row elements are so small compared to the third row elements that even though the electron is going into an energy level that's closer to the nucleus, the electron density in the entire atom is relatively large. And so that increased electron density adds to the electron-electron repulsion of the added electron by the existing electrons, which is going to decrease the Coulombic attraction compared to those in the larger elements. So that's an important trend that we're going to have to know about. I hope this is good for you, and if you have any questions, you can ask them in class tomorrow. I'm also going to see if I can find a couple of videos to post along with this in order to help you identify, help you see some of the trends. And I'm also going to post a couple of videos on taking the alkaline metals and putting them into water, an experiment that I would have done if I had been there. And maybe I can do it during the review, but right now I want you to see what it looks like, increasing the reactivity as you go down from lithium to sodium to potassium and continuing down to rubidium and cesium. Have a great day, and I will see you tomorrow.